So when we earlier talked about covalent bonds, we described them as bonds where the atoms shared electrons, all right? And when you hear that term that the atoms are sharing electrons, it makes it almost sound like they're sharing them 50-50. So the thing about covalent bonds is even though they are sharing of electrons, it's not necessarily true that the electrons are shared completely equally between the atoms. And that's because of this property that atoms have called electronegativity, right? And that is a property of an atom to want to pull electrons towards itself. All right. A way that you can think about electronegativity is just to think of it as greediness for electrons. All right. The higher its electronegativity, the more greedy it is, the more it wants to pull the electrons towards it. All right. You can mark out this little part right here about the blue guide. That was in an old reference guide I used to use. But there are several charts out there that present electronegativity data. All right. And so in fact, here's one of these charts right here. You can see these numbers that are associated with the different atoms, and these correspond to the electronegativities. And you can see here that the most electronegative atom on the periodic table is fluorine. All right, we actually learned about this when we were doing the periodic table. And it's you can see that its value is 4.0, and that's higher than any other value anywhere on the periodic table. Okay, what that means is that no atom is as greedy for electrons as fluorine is. All right, it will win a tug of war for electrons between when it's bonded to any other atom. All right. Again, the more electronegative atoms are going to tend to be towards the right side of the periodic table and also more towards the top. And then as you go to the left side, the electronegativity values are very low. All right. In fact, all of these metals over here, one of the things that makes them metals is that they have very low electronegativity. All right. So we will use these values here when we're in the next topic, which is about bond polarity. So what happens is that if two atoms have a covalent bond between them, all right, and those two atoms have either similar or equal electronegativity, all right, you can basically consider the electrons as being shared equally, all right. But if the two atoms have a significant difference in their electronegativity, they're not going to share those electrons equally, and the bond is considered polar. All right. So if you take this to an extreme, all right, and you have an atom which is really greedy for electrons and one that is extremely ungreedy for electrons, essentially that it's possible that difference can be big enough that one atom will essentially steal that electron from its neighbor. All right, the extremely greedy atom will take the electron from the extremely ungreedy atom. All right, so a couple of examples. So first of all, in that situation where one steals the electron, that's going to lead to what we normally consider an ionic bond. All right, so a couple of examples. All right, if we have a hydrogen molecule, H2, all right, that's just two hydrogens with a single bond. I can look up its electronegativity values from that chart that I just showed. All right, and for hydrogen, it's 2.1. All right, and notice that these are, since they're equivalent atoms, there's there's not going to be one of the atoms that can pull harder than the other. All right, so the electrons in this bond right here are considered to be shared equally. All right. In this molecule right here, chlorine is 3.0, hydrogen is 2.1, and what we can do is we can calculate what's considered a delta electronegativity, all right, a difference in electronegativity. And you just do that by subtracting the two values. And the value here is 0.9. And so that means that these electrons are going to be shared. These electrons right here are going to be shared unequally. All right. Chlorine is essentially, you can think of it, it's going to hog those electrons. It's not going to completely steal them, all right? It's not so electronegative that it can completely pull those electrons away from the hydrogen and basically claim it as its own, but it pulls on it more than hydrogen can pull on it, all right? And we're going to talk about the effect that that has on molecules in a second. Oops, didn't mean to do that. All right, but let's look at the extreme example. Let's take something like chlorine and sodium, and these are drawn as neutral atoms. All right, this is the value for chlorine. Here it is for sodium. We can calculate a difference in their electronegativity. All right, and that works out to be 2.1. All right, and that is a huge difference in electronegativity. All right, so big that essentially chlorine is strong enough, its greediness for electrons is so much that it can essentially steal an electron from sodium, because sodium doesn't really pull on electrons all that much, right? And when that happens, you can see that chlorine now has an extra electron here. It has a negative charge. The sodium that has lost the electron now has a positive charge, and that is, as we were saying, an ionic bond. All right. So just to give you a little guideline for when it's considered polar, nonpolar, or ionic. Right. So you can use this little chart right here as a guide for whether to consider it nonpolar, polar, or ionic. All right. If the difference in electronegativities is between 0 and 0.4, it's considered nonpolar. All right. Keep in mind, there can be a slight difference in the electronegativities and still be nonpolar. It's just one pulls on it a little bit more than the other, but it's still pretty close. All right. When the range is between 0.5 and 1.7, you would consider that bond to be polar. All right. If it's 0.5, you'd say that it's slightly polar. If it's 1.7, you would say that it's very polar. All right. If it's greater than 1.7, that's getting into this range here, where one of the atoms has got a significantly higher electronegativity than the other, so much that it can essentially pull that electron away, making an ionic bond. So let's think about what kind of an effect that would have on a molecule. All right, let's pretend that we have a hydrogen molecule. All right, H2. I could draw its Lewis structure like this right here. All right, and you got to remember what is in the nucleus of a hydrogen atom. It's just a single proton. All right, so I put a proton right here. This hydrogen atom's got a proton in its nucleus, which would be over here, and there are 2 electrons in that bond. All right, remember those electrons are going to be in a cloud going around those 2 atoms. All right, so I've represented those 2 electrons as these 2 minus charges. So let's do this little mental exercise. Let's split this molecule down the middle. And let's take a look at what's on the right side. All right, so remember, if these electrons are shared equally, on average, one of the electrons would be on the right side and one would be on the left side. All right, remember, it's random motion, but like on average, that would be the most likely scenario if they were, if they were being shared equally. All right, so if we cut it down the middle and you take a look at this right side, that's a positive charge, +1 charge from the proton, but a -1 charge from the electron. All right, so overall, this side right here would be would be neutral. All right, same thing could be said about the left side. It would also be neutral. All right, so what this shows is that if you've got a bond between 2 atoms that have similar electronegativity, essentially both sides would be neutral, all right, completely neutral, all right? But what happens if something were to happen so that those electrons aren't shared equally and they're pulled more towards one side than the other, all right? So let's consider the situation right here. Let's just say that 2 of the electrons were on this side right here, all right? In that moment of time, all right, if we draw a line down the middle, you would have an overall, there's a little bit more of a negative charge on this side of the molecule than there is over here. All right, keep in mind, it's not a full -1 charge because this side doesn't own these 2 electrons. It's just that the electrons spend a little bit more time down over here. All right, so what that ends up causing is we'll call it a slightly negative side to that bond, which goes by this symbol right here. That you call that a delta negative. All right, the opposite side that's having its electrons, that doesn't have the electrons, is delta positive. All right, so even though I've shown this on a hydrogen molecule right here, keep in mind, hydrogen would not do this right here. All right, it would share them equally. All right, I'm just doing this to make it easy to see why one end would have a slightly negative charge, because if they were to be more on one end, if you count up all the charges, there's more negative charge on this side and more positive charge on that side. All right, so what effect does that have on molecules? All right, one of the major effects of these little slightly positive and slightly negative ends of the bonds is it causes little areas of attractiveness between molecules. All right, let's say that we have 2 of these molecules side by side. All right, and this end right here is delta negative, and this end right here is delta positive. All right, so even though they're not a full +1 and -1 charge, they're still, they're still even slightly charged areas that have opposite charge are going to have little bits of attractiveness. All right, so there's a slight attraction between the delta negative over here and the delta positive over here, and so they want to stick to each other a little bit. And one way that this shows up in molecules is that they tend to have higher melting and boiling points. All right, I want to point out that there's 2 ways that you can show, that you can highlight a polar bond. All right, one of them is here. All right, the side that's got that is higher in electronegativity and pulls those electrons more towards itself, you represent that with a delta negative, and the side that has electrons pulled away from it is delta positive. All right, so that's one way of doing it. Another way is like this, all right, where you show this arrow with this hash mark, and you show that in the direction that the electrons are being pulled. All right, so since chlorine pulls the electrons more than hydrogen, it's going to pull those towards the chlorine. All right, and you can represent it this way. All right, so one thing about this, when you're drawing these molecules, you're not required, if you're just drawing them casually, you're not required to draw these symbols. These symbols are drawn as a way of highlighting an electronegativity difference. All right, so kind of think of it as like when you're putting a word in bold. All right, you're not required to put a word in bold, but when you do that, you're drawing attention to it. All right, keep in mind that if you're drawing something that has an actual full charge on it, something like a sodium ion, if this is a sodium ion, you have to show, you would be required to show that charge. All right, so let's move on.